Students, in this video I will talk about simple harmonic motion. So let us start. When a body repeats its motion after a regular interval, we say that it is in the harmonic motion or a periodic motion. You would all be knowing about the periodic motion, that if a motion repeats itself, we call it as a periodic motion or a harmonic motion. The interval after which it repeats its motion is called as the time period. That also would be clear to all of you. Now the third part is, if the body moves in the same path to and fro, then it is said to perform oscillations. You would be knowing about the sine and the cos curves. I will discuss about them in when we go further into this. That is also oscillation, because there is a motion to and fro about a mean position. Now, what is simple harmonic motion? Simple harmonic motion, that is a special type of motion in which the particle oscillates in the straight line. The acceleration of the particle is always directed to a fixed point on the line, and its magnitude is proportional to the displacement of the particle and is directed opposite to the displacement. So, I will once again repeat, the acceleration is directly proportional to the displacement and its direction is opposite to it. So, A is directly proportional to minus of the displacement or minus x. So, proportionality is converted into an equality sign by introducing a constant which is omega square. You all know omega is nothing but angular velocity, which is given by 2 pi by t. We'll talk more about this when we go further. So to explain this, I have taken a point O and there are two extreme points A and B. So the motion is happening between O and A to O, O to B and B to O. This I have drawn. And in this case, in all the cases, I have written in the first path while traveling from O to A, the acceleration will be towards the center, it will decrease as x is increasing because the displacement is increasing. So, acceleration is opposite to the displacement, so it will be directed towards the center. In the second case, x is decreasing because the displacement is decreasing, so the acceleration is directed towards the center. In the third case, when it is traveling from O to B, what is happening? The x is again increasing, and as x is increasing, acceleration will be directed opposite to the displacement, so it will be towards the center. And while traveling from B to O, acceleration at C, displacement is decreasing. So displacement is decreasing means acceleration is increasing and it is directed towards the center. So in all the cases, the acceleration of the particle is directed to a fixed point. So this constitutes a simple harmonic motion. We'll come to the example of a simple pendulum. You all know that it oscillates with a simple harmonic motion. So here it's a simple pendulum where its neutral position when it is in the vertical direction, and we displace it with a very small angle theta. Here we assume that the theta is very small. Okay, so what is happening? So L theta small means this L and this L is going to be the same. It is going to be a very small displacement. Now to magnify it, we have made an angle theta. So you can now divide the forces which is acting. There is a gravitational force mg acting on it and a component mg cos theta which will get balanced by the tension force which is acting in the opposite direction above it, and there is an mg sin theta force. There is an mg sin theta force which brings it towards the mean position. So the force is given by minus mg sin theta. But from Newton's second law, we know that F is equal to m into A. Okay, m into A. So m by A, m into A is minus mg sine theta. But sine theta, as we know that it is very small, so this is the assumption we have used. Sine theta will be perpendicular upon half a hypotenuse. So sine theta will be x upon L. We have substituted this value. So acceleration is minus times of g by L into x. Why minus sign is that force is opposite to the displacement but is directed towards the center. So minus g upon L into x. Now if we compare it with the explanation of the simple harmonic motion, what we have given, A will be nothing but minus omega square x. So I am comparing equation 1 with omega square x. So I will get omega square is g by L. Now for a small, revision purpose, I am just saying for a circular motion, in a circular motion angular velocity will be given by 2 pi by t, okay, because the angle which is covered is 2 pi in one circle and the time taken to complete one circle is t, which is a time period, so omega is 2 pi by t, okay. And frequency also you should know, that is the number of oscillations per second, which is a reciprocal of the time period, because t is the time taken to complete one oscillation. So in 1 second 1 by t oscillations will be completed. So equation 2 can now be written as 2 pi by t, which is omega. The equation 2, you know, it is written here as 2 pi by t is the under root of g by L, because omega square is g by L, omega is under root of g by L. Okay. So time period will be 2 pi under root of L by g from this. So you have understood this is a very simple, important, and everybody knows this is a simple equation, but how it is derived using the simple harmonic motions basics is given here. Now simple harmonic motion I am now explaining with the help of a differential equation. If a differential equation is there, how do we understand that it's a simple harmonic motion? We know that A is equal to minus omega square x. A is nothing but acceleration, which we know is a double integration of the displacement. So d2x by dt square is minus omega square x. So I am bringing the right hand side to the left hand side. So the equation becomes d2x by dt square plus omega square x is equal to 0. So wherever in the solution we get d2x by dt square plus omega square x is equal to 0, which means that the motion which will be executed by the body will be a simple harmonic motion. Now if I take x is equal to, we know from the differential equation solutions also, which is a part of mathematics and will be covered when we will talk about the solution of the differential equations. But for the time being, if I take x is equal to a sine omega t plus delta, or if I take x is equal to a cos omega t plus delta, so if I am checking this x is equal to a sine omega t plus delta, I am differentiating it, dx is equal to a omega cos omega t plus delta, and if I do the double integration, which is all part of differentiation and mathematics, so you will understand this if you have the knowledge of the differentiation and integration. So d2x by dt square is minus a omega square sine omega t plus delta. So d2x by dt square is minus omega square a sine omega t plus delta. You can check by doing the double integration, we again get the sine. So sine means a sine omega t plus delta. We know we have defined it as x. So we have substituted this value. So we got d2x by dt square plus omega square x is equal to 0. So this is a simple harmonic motion, and which we know from the definition, and I have told from the differential equation, if any motion comes like this, we say it's a simple harmonic motion. So what does this indicate? This indicates that x is equal to a sine omega t plus delta will be nothing but a simple harmonic motion. Similarly, x is equal to a cos omega t plus delta will also be a simple harmonic motion. Here delta is a phase difference. So we'll talk about phase also when we will cover the chapter of sound and harmonic motions. But for the simplicity of the understanding of this topic, I will take that delta is equal to 0, but there is no phase difference. Means there is no phase. The start of the motion happens from the fixed point. So delta is equal to 0. We are assuming for the simplicity and for the explanation purpose. So I have drawn the graph. So x will become a sine omega t, or x will become a cos omega t. So I have drawn the graph of a sine omega t and a cos omega t. You can see that it is a simple harmonic motion. The motion is repeating after a time period t which we have written. So it is repeating after every time period t, and the maximum amplitude is given by A. So this is a sine curve. So sine curve is nothing but a curve of a simple harmonic motion, and the mean position, you see that the 0 from where we are starting is called as the mean position. Here now I have drawn the curve for a cosine curve also. The only difference is that it is starting from the extreme position rather than starting from the mean position. So this is also a cosine curve, which is a simple harmonic motion. Now another important thing is you should understand what is the relation between the displacement and the velocity at any particular point when the displacement is x in a simple harmonic motion. So for using simple trigonometry, x is equal to a sin omega t, and the velocity is nothing but differentiation of the displacement, which is dx by dt, so it will become a cos omega t. I have substituted the value of a cos omega t as under root of 1 minus sin square omega t, keeping a as outside, and sin square omega t will be nothing but x square by a square, which is evident from this equation. So it will become omega a under root of a square minus x square by a. So we get an important relation between the velocity and the acceleration, given that the maximum amplitude of the simple harmonic motion is a. So v is equal to omega times of under root of a square minus x square at any particular instant. Now, I will bring an example of a spring mass system, which is also a simple harmonic motion. You see that I have made a spring with a magenta color and a mass m. Now, if I compress it, what will happen? It will move a distance x, which I have drawn from the blue line, and the spring gets compressed. When the spring gets compressed, it forces the mass to go out. The displacement is acting. The displacement is happening in this direction, whereas the force is acting in this direction. So what is happening? F is nothing but minus k into x. Both are in the opposite direction. So F is equal to m into a will give a is equal to minus k by m into x. Here you say that acceleration is again directly proportional to the displacement and opposite to it. So it is matching the equation or the definition of the simple harmonic motion. So omega square will become k by m, and time period will be given by 2 pi under root of m by k, as t is equal to 2 pi by omega, which we have explained above. So hope this would have been clear to you. I'll cover one more important thing. What will be the total energy of the spring of the mass when it is compressed by a distance x? So you should understand, we have derived the relation v is equal to omega times of under root of a square minus x square. Kinetic energy of the mass at x displacement is given by half mv square. You know this formula. So half m omega a square minus x square whole square. So I have solved this. So kinetic energy at any displacement x will be given by half m omega square a square minus x square. But what will be the potential energy? Potential energy of the system, we already know it will be half kx square. When any spring is compressed by a distance x, the energy stored in it will be half kx square, or the work done by the spring will be half kx square. So half k values you can understand. K value is nothing but from this equation. K value is m omega square. So I have substituted k value as m omega square. So I got this kind potential energy formula, which is half m omega square x square when the compression of the spring is x. So the total energy will be kinetic energy plus potential energy. I have added these two terms, x square and x square gets cancelled. So we get the total energy will be half m omega square a square. For this short video, simple harmonic motion, this is sufficient. We will cover more examples of the simple harmonic motion in our next video. Thank you. Hope you will understand and like this.